morning, everyone. We're here to present on deadlock detection and recovery, a key concept in operating systems. My name is Andani Patni, and with me is Zahra Fatma and Ashmit Vedant. Let's begin by understanding what a deadlock actually is. A deadlock occurs when two or more processes are each waiting for a resource that another process is holding on to, meaning none of them can continue. This usually happens in systems where multiple processes share limited resources. The result is that all waiting processes get stuck indefinitely, which can lead to low CPU utilization, system freezes, and sometimes even data loss. For example, imagine process A holds on to the printer and is waiting for the scanner, while process B holds on to the scanner and is waiting for the printer. Since both are waiting for each other, neither can proceed, thus creating a classic deadlock situation. To visualize this, we can use an example of a one-lane bridge that allows cars from only one direction at a time. Now, if car A enters from one side and car B enters from the other, and both meet in the middle and stop, neither can move forward or move reverse. This situation perfectly mirrors a deadlock situation, where each car represents a process that is holding on to one resource and waiting for another. Just like traffic halts on this bridge, process execution halts in a deadlock situation. There are four conditions that are necessary for a deadlock to occur. Mutual exclusion, where at least one resource must be non-shareable. Hold and wait, where a process holding on to a resource can request additional ones. No preemption, where resources cannot be forcibly taken away, they're only released voluntarily. And circular wait, where a circular chain exists where each process waits for a resource held on by another process. If even one of these conditions can be prevented, a deadlock can be entirely avoided.
Introduction to Resource Allocation Graph. To analyze and detect deadlocks, the operating system uses a tool called the Resource Allocation Graph or the RAG. It is a visual way to represent how resources are assigned to processes. In this graph, processes are shown as circles, resources as squares, and edges indicate requests or allocations. This makes it easier to see which process is waiting for which resource and helps us spot potential deadlocks more clearly than tables. Dynamic nature of RAG. The resource allocation graph is dynamic, meaning it changes as the system runs. When a process requests a resource, an arrow is drawn from the process to the resource. Once the resource is allocated, the arrow direction reverses. Now it goes from the resource to the process. When the process releases the resource, the arrow disappears. This constant change reflects the real-time state of the system. How RAG represents the system state. The RAG helps the operating system to visualize whether the system is in a safe or unsafe state. If there is no cycle in the graph, the system is safe, meaning no deadlock. If there is a cycle and a resource only has one instance, a deadlock has definitely occurred. If there are multiple instances of resources, then a cycle only indicates a possible deadlock that needs further checking. Deadlock detection. So how do we use this graph to detect a deadlock? First, the operating system builds a resource allocation graph from the current resource and process data. Then, it uses a graph traversal algorithm such as depth first search or breadth first search to look for cycles. If a cycle is found, the processes involved in it are identified as deadlocked. This method is widely used in operating system schedulers and database management systems to manage resource allocation efficiently.
Periodic monitoring. Detecting a deadlock once isn't enough. The system needs to check for it regularly. That's where periodic monitoring comes in. The operating system runs deadlock detection algorithm at a set intervals of time to analyze current allocation and requests. This ensures that any potential deadlock is identified early before the system halts. In high concurrency environments like servers and database, this continuous checking is essential to maintain high performance and prevent slowdowns and shutdowns. Recovery importance. Detection is only half the solution. The recovery is what actually gets the system running back. Once a deadlock is detected, recovery ensures that every resource are freed, halted, processes are resumed, and data remains consistent. The goal is to restore the system with less data loss and minimum downtime. Efficient recovery prevents cascading failures and ensures a smooth user experience even after a deadlock occurs. Now, recovery by termination and resource preemption. There are two main ways to recover from a deadlock. The first is process termination. We can either terminate all the deadlock process which is fast but risky, or terminate them one by one, which is slow but safer. The second approach is resource preemption, where the system temporarily takes resource away from certain processes and reallocates them to other to break the deadlock. However, preemption must be handled very carefully to avoid starvation, where the same process keeps losing the resource. Modern OS use fairness algorithms like aging or priority rotation to prevent that. Now we move on to the case study, printer and plotter deadlock, with its pros and cons. Let's look at a quick example. Suppose process 1 is holding the printer and requesting the plotter, right? Process 2 is holding the plotter and requesting the printer. The system detects this circular wait in RAG P1 to plotter to P2 to the printer back to P1, confirming a deadlock. To fix this, the OS can preempt one resource, say the printer, from P2, break the cycle and allow both to proceed. While RAG is an excellent visualization and teaching tool, it can also become very inefficient in large systems with hundreds of processes running, as maintaining real-time graph increases CPU and memory overhead. So it is very useful but not ideal for large-scale multi-instance system. And with this, we conclude our presentation on deadlock detection and recovery. We hope this gave you a clear understanding of how deadlock occurs, how they are detected, and how the system recovers from them. Thank you from all the team.